Welcome to Lecture 20, entitled Surface Integrals. In this case, we're going to be looking at scalar functions and the computation of flux using the explicit representation. And again, this material is coming from Reading Assignment 4, Section 1.6. The objective in this case is to compute the integral of a scalar density over a curved surface and a flux in 3D using an explicit representation. The concepts and visualization skills associated with this lecture include mapping from a planar surface in the XY plane to a curved surface. In the last lecture, we were going to a UV plane. Now we're actually dealing directly with the XY plane. The Riemann sum in this case, the construction of a differential surface area vector, and computing the magnitude of the differential surface area vector. As usual, the second slide is just an outline of the presentation to follow, so we will just skip over it. All right, so now what we'd like to do is an example representing the explicit representation of a surface, in which case the variables of interest in surface integration are in fact the original variables, which are x and y. And so for this particular example, the objective is to map out points on a planar surface region R in the xy plane that point to points on a curved surface region defined by z equals square root of x squared plus y squared within the range of z with lower limit 0 and upper limit 4. And so in this case, the diagram that we'd be looking at is the one shown below. And it's this exterior surface of the cone to the apex point to the top here that we're interested in. That's the region S. So first thing is to establish a position vector, but in an explicit arrangement, it's very simple because essentially the surface is in fact the function z. So you've got the variable x, variable y, the function of z, which is a function of x and y. But in this case, the region is simple to see because it's more or less a projection of the surface onto the xy plane. So if you look at this, the maximum extent of this cylinder is when z is equal to 4. But when z equals 4, that's equivalent to saying that x squared plus y squared equals 16, which is equivalent to a radius of 4 for this upper circle. Well, if you project that down onto the xy plane, then the region of integration, which involves limits on y and x, is in fact defined by this purple region, region R, which is the circle. And so just by inspection, you can see that the integration bounds for y would be this half circle, and for the lower integration bound would be this lower circle. Well, the upper circle represents square root of 16 minus x squared, whereas the lower circle represents minus 16 minus x squared. The bounds on x would be from x equals minus 4, which is a line on the xy plane that's in the y direction, passing through the point x minus 4, and another line passing through the point x equals 4. So these become the bounds, upper bound, lower bound for the x integral, and the upper and lower bound for the y integral. So this is more or less the setup that we have in terms of setting up the position vector, which maps out every single point on this region, but at the same time, these bounds now also reflect the integration bounds that we'll be choosing. Okay, so given that we have set things up, then we want the explicit representation of a Riemann sum. So scalar function and flux we were interested in, as we were with the case of the parameterized representation. So in this case, we're parameterizing with respect to the variables x and y. So the charge density at any given point on the surface is related to x, y, and z, which is the actual point on the surface. Evaluate x and y. This is the explicit representation of the function of the surface. In the limit, basically, as you make the surface area elements smaller, and you need more of them to fill out the space, this in the limit becomes the double integral of sigma x, y, z, where z is valued at xy ds. Delta sk in this case will be txk cross tyk magnitude, delta x, delta y, and the differential charge associated with a specific surface area element now will be xk, yk, z evaluated xyk, delta sk. So this is a differential charge. And again, the units of sigma are coulombs per meter squared, which is the charge density. In the limit, delta becomes d. So this ds is the magnitude of t subscript x cross t subscript y. dx dy. In the case of flux, we're taking the dot product between the vector field at a given location times the differential area at that location, and you're summing over all differential surface patches. And in the limit, you end up with the total flux and this double integral. So f of k basically would just be the coordinates of the vector field, but now the coordinates are with respect to x, y, and z, where z is a function of x and y. So this is the x-coordinate, the y-coordinate, and the z-coordinate for the vector field f. In the limit, then, this is just a continuous function. It's not looking at individual differential areas, basically indexed by the subscript k. Here it's just a continuous function. And this is the flux density. So delta sk in this case would be t delta xk cross ty subscript k delta x delta y. It's a differential area vector. And this is the differential flux associated with the differential area. The units of f of k will be some symbol, number, flux divided meter squared. So in this particular example, the property could be the current in amps, for example, in which case this really ought to read current flux. Okay, they normally would say current, but in actual fact, we would say current flux. That way you know that we're dealing with a vector field rather than a scalar. Okay, so the word flux tells you vector. All right, in the limit, the delta s at k becomes ds, and it will be just tx cross ty dx dy. Okay, so let's take this example and that we just dealt with earlier and just work it out for a given situation. We're talking here about a thin sheet described by the surface z equals square root of x squared plus y squared. For z, 0 less than equal to z is less than equal to 4. And the density of the sheet in grams per centimeter squared, this is CGS units, is rho equals fxyz equals 8 minus z. Compute the mass of the cone. So this is a surface density of mass on this cone, and we want to know what the total mass of this cone is. So again, step 1 is parameterization of the surface, and that's just going to be position x, y, and z is a function of x and y. We know what the z value is. It's just square root of x squared plus y squared. So here's our position vector. And the region over which this occurs would be from minus 4 to less than equal to x is less than equal to 4. And for y, it's between minus square root of 16 minus x squared and root 16 minus x squared positive. And so this defines this purple region. This is purple region is nothing more than the projection of this surface area onto the xy plane. So step 1 completed. All right, so let's continue on. The second step of the calculation process is to compute the magnitude of the differential area ds, which by definition will be the magnitude of tx cross ty dx dy. So let's look at the individual calculation steps here. First of all, the position vector, which maps out the surface of this cone, would be just x, y, and z, of course, where a function x, y would be the equation of this cone, which is shown here to be square root of x squared plus y squared. And so there it appears as a z in this tuple. All right, next step is to compute tx, which is just taking the derivative of the position vector with respect to the variable x. That'll give you 1 there, 0 there, and then this will give you x over square root x squared plus y squared. Similarly, we basically compute t subscript y, which is by definition going to be dr by dy. In this case, this will give you 0 for the first term, 1 for the second term, and y over square root of x squared plus y squared, square root. Next step is to take the cross product between these two vectors. In sort of an absolute sense, it's just minus dz by dx minus dz by y, 1. We could have actually worked this out and gotten the same expression as shown here. If we take this as being z and you take derivative with respect to x, you'll end up with x over square root x plus y squared. Similarly, dz dy will give you y over square root of x squared plus y squared, but both of these have to be multiplied by 1 to give you basically, and a 1 to give you this expression. Now the question is, this vector being perpendicular to this conical surface, is it pointing inwards or outwards? Well, 1 basically means z is pointing upwards, which means the vector is pointing inwards towards the z-axis, right? So this is basically inwards. If it turns out that we want it to be outwards, we would just multiply this whole expression by minus 1, in which case this would be in a positive quantity, a positive and negative, and then vector would be pointing outwards from the conical surface. All right, now that we have dx cross dy, next step is to take the magnitude of this expression times dx dy, which is the magnitude of the differential surface area of any given element on the surface. And so all we're doing now is to take the more generalized form, which is just 1 plus dz dx squared plus dzy d squared square root dy dx. And you can just, by taking this expression here, take the square root of the magnitude. This will just be x squared over x squared plus y squared over x squared plus y squared plus 1. And then basically you basically multiply through top and bottom on this side by x squared plus y squared and add the results and take the square root. You'll end up basically with a square root 2 factor. X squared plus y squared cancel in the numerator and denominator. So now we have ds in terms of root 2 dy dx. And the last step is to compute the surface integral of rho ds. So we have rho, which is parameterized in terms of x, y, z, x of y. This was 8 minus z, but z basically is the surface x squared plus y squared. And we have basically the expression for ds, which is this. And now we make the substitutions. So rho x, y, z of x, y becomes this expression. This here becomes this expression. And the bounds in Cartesian coordinates would be between minus 16 minus x squared square root and positive 16 minus x squared. Lower limit minus 4 and 4 for x. All right, so one could do this, but it's simpler to convert to polar coordinates. And if you convert to polar, that means the Jacobian will be r, and you'll end up with r d theta. X is r cos theta, y equals r sine theta, so this term just becomes 8 minus r. And this is basically just the upper half of a circle, lower half of the circle. And it's a radius of 4, so radius will be from 0 to 4, and you're sweeping once around the whole circle, so it's 0 to 2 pi. And the root 2 basically is being taken outside. This is a simple integral to calculate, and you'll end up with an answer of 379. All right, so the last example is rain flux on a slanted roof. So in this case, the problem statement is to compute the flux of rain hitting the slanted roof. The flux density is F equals 0, 0, minus 1, which means it's downwards. Direction across the surface, which is the plane is Z equals 4 minus 2x minus y in the first octave. All right, so this is the equation of the plane. And so the region that we'll be interested in is a projection of this section of the plane, which in the first octant, onto the xy plane. And that projection leads to this gray triangle that you see on the xy plane. So the parameterization of the surface is relatively simple. We have xy, and the z component is more or less the equation of the plane. We're only interested in the first octant. So we're interested in x from 0 to 2. 2 would be this point here. And y, limits on y would be y equals 0, which would be this line. And this line here, which is just the equation y equals 4 minus 2x. So the bounds basically for the double integral now are set between 0 and 2 for x and between 0 and 4 minus 2x for y. The other thing we have to keep note of is the fact that the flux is downwards. So if we want a positive value, we want to choose a surface area vector which is also pointing downwards. So when we take the dot product between the two vectors, we get a positive quantity. So the problem statement, in effect, tells you in what direction the surface area should be pointing. Okay, so complete the rain flux on slant roof. The next step is basically to compute ds, the vector. That's the differential area. It's dx cross ty dx dy. We've already have r, the previous slide. It's this expression. Now we take the derivative of this with respect to x, and we end up with this expression. Derivative with respect to y, we end up with this expression. Next step is to take the cross product. Again, this means that you set up the matrix and take its determinant, and you'll end up with this expression here. If you then take the derivative of z, which is this with respect to x, you basically will get a minus 2, but you have a negative here, so this becomes a positive 2. dz with respect to y would be minus 1, but you have a minus 1 here, so this becomes positive 1, and you have 2, 1, 1. All right, but this is a direction z is 1, would be upward. We don't want upward, we want downward, which means we have to multiply this through by negative 1 to essentially rotate it by 180 degrees. So the correct direction for the surface area vector is minus 2 minus 1 dx dy. So the last step is now to compute the integral f dot nsds. This basically is equivalent to just ds. All right, so we're given basically the vector field, which was 0, 0, minus 1. We now have the surface area vector differential, surface area pointing downwards. We've chosen the iteration integral to be dy followed by dx. Why? Because the region is structured in such a way that the limits on y are between 0 and 4 minus 2x. So that means y has to be a function of x, so it has to come first. And then the last bounds, the outer bounds, are for x between 0 and 2. So if you perform the dot product, then you get a 0 contribution for the first term, 0 for the second, and the last one will give you 1. So that means dy dx. That's why you end up with this. And the rest is just a matter of taking the integration and taking it to its conclusion, and the result is the flux being 4. All right, so this would be a mass flux. Okay, so mass flux would be in terms of kilograms per second per meter squared. Okay, that's the amount of rain that's hitting that would be the flux density in terms of amount of rain that's hitting the surface, and we would be computing it over the full surface area. So we'd be talking about kilograms per second of rain that has to be basically removed by the gutter system. All right, so we have now just a quick couple of pictures sort of summarizing various possible surfaces that you might encounter. And I'm going to give you a slide which has the explicit description and also a parametric description of the same 4 different types of surfaces. I'm not going to go through this. It's in the notes, but it's something here that's quite useful. So for instance, what you have here on this column are the equations describing the surface. If we're using an explicit description and you're dealing with surfaces which form closed contours, you need to basically describe in terms of 2 different surfaces. So for example, here you have the right half represented by this. This involves a square root, and the left half basically needs a minus square root. All right, there's no way basically of describing this using a single function when we're dealing with an explicit representation of the surface. Anytime you have a square root, you know you're going to have basically to deal with 2 parts. So here's another example: the upper hemisphere and the lower hemisphere. So if you have all the information, then you can basically compute tx cross ty, and so that's what I've done. This is the expressions that we need to develop, and then these are the specific examples, for this case, for this case, for this case, and for this case. Okay, for parametric description, it means x, y, and z as described in terms of variables u and v, and in this case, you can see here, for instance, with u and v, we can represent a closed contour with just a simple parameterization with limits on v and u. So these are the same 4 examples as in the previous slide, but using parametric description of the surface rather than explicit description of the surface. And so if you follow through, you'll end up clearly with different expressions, but when you do the integrals, you'll end up exactly with the same answer. All right, so let's just a general summary in terms of computing surface area integrals. And a question that quite often arises is, how do you determine if a parametric or explicit description of a surface is the best choice? And so I've given 3 answers here. First is that if the surface is given explicitly as z equals f as a function of xy, then generally the explicit approach is the best choice. On the other hand, if the surface is a closed smooth surface, then the parametric approach is the best choice. Of course, you could use an explicit approach, but then you would basically quantify the top half of the surface in terms of a positive square root in the sort of the general cases that we'll be looking at, and the lower half of the surface by the negative of the square root of a function. Of course, it can be more complex looking functions, but generally you have to split it into 2 separate surfaces. You cannot basically parameterize it in one go. And the third option is this: if neither option 1 or 2 apply, and the reader must experiment to see which of the 2 approaches is easier. Generally, the problem is stated in such a way as to explicitly state the choice to be made, or by inspection, it is obvious which approach to choose. Okay, and so the last slide now is just trying to group together all the equations that we have basically described over the period of this lecture and the previous lecture, sort of in one common place. And so we have the starting point, which is a position vector. the vectors defining the tangent plane, the unit vector that's normal to the tangential plane, ds being the magnitude of the differential area, and ds being the differential area vector, which is the unit vector times the magnitude of the differential area, which is the same here. And so we had the parameterized representation, and so I basically just sort of summarized them here. And we had the explicit representation, and I basically summarized them here. What I haven't mentioned here that not only do you need the parameterization, but you also need the bounds on u and v in this case, and the bounds on x and y in this case, because those bounds are the ones that you use for the bounds on the double integral. So here I've just sort of looked at the case when you're dealing with integration of a scalar function over surface area. And so here it's written out basically in a parametric form, and here it's written out in an explicit form. And if we're dealing with flux, which is a dot product between the vector of some vector and a differential surface area, then this is the way I would write it if I'm dealing with a parameterized representation of the surface. And this is the way I would write it if I'm dealing with the explicit representation of the surface. And again, just to remember here, there are two options for the surface area, pointing upwards or downwards. The problem statement or convention will dictate which version to adopt. Right? So that more or less concludes Lecture 20. Thank you for listening.